So there's two words that probably in the thesaurus sound the same, but we mean something differently. Verification means, did you build the thing right? And this is, did you meet the specification? Validation means, did you build the right thing? That is the customer happy? More or less, this means is the specification correct, right? So pretty much hardware deals with verification. There's a spec. It's not going to change. It deals with it. Software, maybe not NASA software, but most kinds of software generally deals with validation. Did you build the right thing, right? Not the thing right, but the right thing. And this is one of the why software is hard, is the customer will change their mind what they want. So Agile is about validation. And so there's two options to go forward here, and there's testing and formal methods, and we'll talk about both of them. Exhaustive testing is infeasible. We hope to get a tablet thing working here, so I'll just do this in my head. Let's say we had one 64-bit number. Okay, one input, just one input, 64-bit number. And let's say we can do the test in a nanosecond. All right, you can execute like 4 instructions. That does the whole test. What a wonderful world that would be. So let's multiply this out. Let's see. 2 to the 64 combinations. A nanosecond is like 2 to the 30. So if I divide, that's 2 to the 34, okay? So it turns out, this is a very useful piece of information, there's about 32 million seconds in a year. You'll find that useful. So 2 to the 25th seconds in a year. So divide by 2 to the 25th, what we end up is 2 to the 34th divided by 2 to the 25th, that's 2 to the 7th. That's 500 years. So if you could do the test in a nanosecond, and it's one variable, it'll take you 500 years to do exhaustive testing. So you can't do exhaustive testing, right? Your programs probably have more than one variable, and it probably takes more than a nanosecond. So you can't do that. So what do people do? What we always do in computer science, we divide and conquer. We perform different tests at different phases of software development. And we're going to build up, right? Layers of interpretation, layers of abstraction. That's our standard shtick here. And what we're going to do is you're going to do some testing at a low level, and the levels above it are going to assume they've done that right testing and go ahead. So at the bottom level, it gets called unit testing. So you're testing typically a single method to see if it did what expected. So that's one method at a time. The next level up from that is either called module testing or functional testing, where you're testing across a bunch of units. Okay? That's another type of testing. Integration testing, it's above the module, interfaces between units. Make sure the assumptions are correct and they can communicate. That's the part you're testing, integration testing. And at the top of the stack is either called system test or acceptance test, where the integrated programming seeing if it meets its specifications. So that's the names for the different types of tests. So this is the strategy you would use. And we'll do that in this class. We're going to have a tool that's just designed for unit tests and tools that are designed for these upper levels. The Ariane 5, they didn't do system level testing on that, right? They did these lower level tests. Yeah, that module worked, that module works. They didn't try running the rocket when it went over the full distance, and that's why they debugged it the other way. There's a lot of stuff written about testing. Coverage is percentage of the paths covered. So if you think of conditional branches, how do you change the variables? Have you touched all of the paths in the program? Regression testing is this idea, you're evolving the software over time. If you might add something and break old tests, how do you avoid that? Well, you run the tests continuously or repeatedly. Maybe overnight you'd run it. And there's another phrase called continuous integration testing, which really is continuous. So with modern services today, there's a service that you could use that will do continuous integration testing for you. Will be constantly running these tests against the software as you evolve it. And then, as we said, the relationship to Agile to this, a big part of Agile is test-driven design. You write the test before you write the code you wish you had. So you really do that in this course. And as Armando says, because Armando actually builds code, it seems unnatural to do it this way. Why are you doing this? But once you've done it and you see the benefits of it, it becomes the way you go forward. But there's limits to testing. This is our next Turing Award winner, Egstra Dijkstra. He's kind of an ornery guy, Egstra Dijkstra, but he wrote, maybe because he's ornery, he has very pithy sayings that he does there. He says, program testing can be used to show the presence of bugs, but never to show their absence. All right? You can find bugs, but you can't prove they're not there with testing. So another approach is called formal methods. How many of you have already been exposed to formal methods? Not much. Okay. You start with a formal specification. I actually did this in my dissertation. It was about a lower level of programming. But you take this formal specification and you prove the programmer follows the spec. So you're writing proofs out. So you're not doing any testing. You're seeing if the code matches the spec. One person you do it by, a person does it, but that's so tedious that's not done very often. There's two approaches to do it by computer. One is automatic theorem proving. You can use the spec and the code and be able to get theorems that you could have to prove. You do that from scratch. And the other part that's more popular recently is called model checking, where you're looking for some features to see if it's, you search all possible executions for just a limited set of features. And that's computer model checking. So people do use this, but it's really expensive to do. So what does it work for? Well, if it's really small examples, since it's so expensive, you better only use it when it's hard to change, so it's expensive to repair, very hard to test, and it gets used for network protocols and safety critical software. So what do I mean by expensive? The biggest program that's been formally verified is a small OS kernel with less than 10,000 lines of code. It costs them about $500 a line of code. To put that in perspective, NASA software, which is really expensive, is $80 a line of code. So it's tremendously expensive compared to most kind of software today. This course is about rapidly changing software, easy to repair, easy to test. We're not going to talk about formal methods, but at least you need to be aware of it. And when we get into the future, we'll talk about it.